Good morning, everybody. Let's get started for the day. So there is a question about when we are going to have our office hour, special office hour for the final exam or before the final exam. As it turns out, we are going to have office hours on during the next class. So today I'm going to talk about hypothesis testing and confidence interval for two populations. Okay. Hypothesis testing and confidence interval for two populations. So two population proportions, two population means, and standard deviation, we probably won't do it. Just these two. And then on Wednesday, day after tomorrow, we are going to have the entire class review session. Okay. Entire class will be review session for the final. I already have put the review for the final exam online. I strongly recommend that you go over the review problems and bring in your questions on Wednesday. So the entire class session on Wednesday, I'll be just taking your questions, and I would strongly recommend that you go over the problems and collect all the questions. Look at all the problems in the review sheet, try to solve them, and collect all the problems where you're having difficulties. That way you will get the most out of this review session. On the other hand, if you just show up for the review without having to look at the problems previously, you'd not know what to ask. And the things that I try may not even make sense to you. So it is very important that you go ahead and try the review problems beforehand. So that's the first thing. So our review session would be on Wednesday. Now, based on the need, okay, so the final exam is on Friday. Sorry, not Friday, Monday, a week from today. A week from today on Monday at 6 a.m., I'm going to open the final exam. And then you will have probably a couple of days to work on it on the final. So maybe Monday, Tuesday, and part of Wednesday, maybe. So you will have a couple of days to work on it. So depending on how things go, I might have a review session Sunday night, special review session on Sunday night. It depends on how things go, what kind of questions people have. So I try to get the review going by Wednesday. So everything should be done by Wednesday, but depending on how things are, I might have another special office hour for the final exam. Okay, that's what it is. Now let's see, Jonathan, does it answer your question about review session for the final?
Yes.
Okay. This is final. I don't want to wait until the very last moment for the review. I kind of want you to look at the problems beforehand. So if I hold the review session on Sunday night, that kind of is too late because there are a lot of materials that we have covered over the semester. So Sunday night would be a bit late. So let's do it on Wednesday. This Wednesday, the entire class. You'll have 2.5 hours or 2 hours and 45 minutes. Okay. All right. Any question about anything else? Final exam is going to be comprehensive. Everything that you learn from day one of the semester up until everything that I cover by the end of today's lecture. And it should be very straightforward, kind of like the midterms that you have taken. You have taken 2 midterms so far. That should give you an idea about the structure of the final exam. Okay, is very much same. And during the final, It doesn't have to be taken in one stretch. You can take, work on the final for a little bit and get out and come back and work on it during the window of time when it's going to be open. All right. Okay, now let's go ahead and start talking about hypothesis testing for two population proportions, or two populations rather. So we are going to do hypothesis testing, and in the process, we are going to do confidence interval as well for two populations. And as usual, we could do hypothesis testing and confidence interval for population proportion, hypothesis testing and confidence interval for population mean, and hypothesis testing and confidence interval for population standard deviation. We are going to do hypothesis testing and confidence interval for population proportion, and then population mean, which is two cases when you know sigma and when you don't know sigma. And population standard deviation, I'll skip it. This is not part of the syllabus. Hypothesis testing and confidence interval for population standard deviation. But I actually did it for single population, even though it was not part of the curriculum for this course. So for the two populations, I'll just skip it. I could do it if you wanted. They'll give you a little extra materials, but just to help you guys out, I'll just skip this one. Now, hypothesis testing for two populations become interesting study in comparing multiple groups. Okay, you compare multiple groups of people or multiple groups of items or things. Okay, now one very interesting example could be whether men smoke a higher percentage of men smoke compared to women, or vice versa, right? Or whether a higher percentage of women smoke compared to men. Whether a higher percentage of African Americans are being pulled over by the law enforcement agencies compared to other races. Comparative studies. So remember, hypothesis testing for two populations is basically comparative studies. Things are interesting when you compare two or more populations. By the way, we have hypothesis testing for two populations, then we could do hypothesis testing for more than two populations, okay? And when we do more than two populations, we have different distribution, F distribution, and some other distributions that we talk about. But we are not going over those, all right? But conceptually, the main thing is hypothesis testing, confidence interval for single population. Once you understand that, which we went through in details, the other things are kind of derivation of these things, the concepts that we have learned. So it's nothing really complicated. The main thing is to ensure that you understand it for single population. Now, is there a difference in percentage of American students that go into engineering field versus foreign students? So you can do a comparative study between the American students and foreign students. What percentage of them attend engineering schools? Is there a gender differentiation in hiring for certain type of job? Okay. Are immigrants more prone to work harder compared to Americans who grew up in the US? Very interesting comparative studies. Are people of certain ethnic group more likely to develop certain diseases compared to other? So if you are Mexican American, are you more likely to develop diabetes? Or because of the food habit or dietary habits? Or compared to, like, if you're Asian American, are you more likely to develop certain diseases such as diabetes? Okay, or if you're African American, are you likely to develop more heart problems? If you are Caucasian, are you more likely to develop skin cancer if exposed to sun? So these are comparative studies. So it's not about just social issues. It could be about health and well-being or medical science, or it could be about pretty much anything that is of interest to you. Now, when we are doing hypothesis testing for two populations or confidence interval for two populations, again, we go through the exact same thing that we did for single population. We do the normality test, okay? Make sure that it's bell-shaped. Instead of one population, here we do ensure there is bell-shaped for two populations. Now, here, please change this number to 10. I don't know, somewhere I found this number 5 in one author that may have been used, and I kept repeating this. So just change it to 10, okay? And this is technically, and P is 10, and Q is 10, but sometimes we don't know what is P, okay? In that case, we use P hat or expected value. Expected value. That means expected number of successes. That means if you surveyed somebody, a bunch of people, is the expected number of successes more than 10? Okay. Then our null hypothesis is, one more thing, very important, that population proportions or populations that you're dealing with are independent of each other. That means one does not depend on the other. One way to compare approximately men and women could be independent, okay? Or one group of people versus another group of people could be independent. When you are comparing American something versus, let's say, African something, okay? Or American something versus Indian something, okay? So those groups of people can be considered independent. However, think of the scenario where you are comparing two groups, but groups are somewhat dependent on each other. Let's say an individual's weight before the person goes through a rigorous exercise program versus the same person's weight after the program. An individual's weight before the person goes through a rigorous program, exercise program, and the same person's weight after the rigorous exercise program. So these two weights are dependent on each other. They're connected to each other, so they are not independent. So we'll be doing something like this where things are dependent towards the end of the class today. So now let's go ahead and kind of go through this. So independent, so populations are independent. Now for null hypothesis, we are going to have P1 is equal to P2. That means the proportions that we are dealing with are the same, okay? Alternative hypothesis could be P1 is greater than P2, P1 is less than P2, or P1 is not equal to P2, okay? P1 is greater than P2, P1 is less than P2, and P1 is not equal to P2. All right. So these are the three scenarios. Now, of course, as you can guess from the naming convention, P1 is the proportion of first group, P2 is the proportion of the second group, or P1 is the proportion of the first population, and P2 is the proportion of the second population. Okay. All right. Next, the test statistic. This looks a bit messy, but I'll explain it to you. Okay. This term is going to be 0. If P1 is equal to P2, then P1 minus P2 is equal to 0. So this is going to be 0. Then P1 hat, P2 hat. There's the sample proportion for population 1. There's the sample proportion for population 2. Okay. And then P hat q hat divided by n1, p hat q hat divided by n2 square root of it. And p hat is defined as this x1 plus x2 divided by n1 plus n2, and q hat is 1 minus p hat. And all these things are going to make sense. This is rather quite easy, even though it looks a bit kind of involved with formula. If you have done the hypothesis testing for population proportion, single population, then you know everything. You just have to crunch the numbers, and that's it. There is nothing new here. And once you find the test statistic, what do? You find the critical regions exactly the way you did. And then based on your test statistic, you make the conclusions. And you can do the p-value as well. I may talk about it here somewhere. P-value. Very simple. Very straightforward. Nothing out of the ordinary. If you have kept up with the material so far, this should be a breeze for you. Even though it looks kind of involved in terms of formula, it is not really. So we'll go ahead and work on these problems. I'll have to go back and forth on the screen to remember these formulas. Oh, okay. The confidence interval is pretty easy. P1 hat minus P2 hat plus or minus the margin of error. And margin of error is given right here. Very simple. Okay. That's it. It's quite straightforward. I have walked you through the important parts of hypothesis testing step by step in the last couple of months. Okay, confidence interval. Now you should be well prepared for this. Okay, smoking rate between two groups of women. You are curious about whether there is a difference between the smoking rates among white women and Mexican American women. So you took a sample, a simple random sample of 100 white women and found that 15 of them smoked. So 100 white women, 115 of them smoked. So while among a simple random sample of 150 Mexican American women, you found 12 smokers. At 5% significance level, remember, at 5% significance level, can you reject the null hypothesis that smoking rates are the same for both groups of women? You need to test whether the smoking rates is the same for Mexican American women versus white women. That's what it is. Okay. Also justify your conclusion by creating a confidence interval for the difference of two population proportions. Okay. So we are going to do it using hypothesis testing, right? And then we're going to come to the same conclusion using confidence interval. Hypothesis testing and confidence interval. Okay, so now let me give you a sense of the numbers. Okay, let me give you a sense of the numbers. So you're comparing, the broader picture is that you're comparing two populations. You're comparing the proportions in the first group with that of the second group. So let's say, labeling wise, group 1 is the white woman and group 2 is the Mexican American women. It doesn't matter which way you label it, okay? Group 1 could be Mexican American women and group 2 could be white women, all right? It really doesn't matter. Ordering of the groups does not matter. So group 1, how many people? So that's your N1. That means the number of white women you surveyed is 100. Out of those 100 women, how many were successful? Meaning success in this case, how many you found to be Smokers, 15. That is your X1. So N1, X1, that goes with population 1. And 1, X1, that goes with population 1. Now, N2 is the number of women that you asked from the Mexican American group, and these are random. And X2 is out of those, how many have said they smoked? And your alpha significance level is 0.05. Okay, so these are the numbers that you're going to be dealing with. Now, let me go ahead and go through the steps of hypothesis testing for this problem step by step, and you should be able to follow along. So just identify the N1, X1. N1 is the population 1's sample size. X1 is the population 1's responses or success. N2 is the sample size for the population 2. That means how many people you surveyed. And X2 is the success rate or the response rate. How many people in the second group agreed or disagreed with whatever you are trying to test, okay? In this case, we are trying to find smokers in the second group. Out of 150 women, how many actually smoked? That's what we are talking about. Now, let's go ahead and work on the problem. Step 1, assumptions. You know, what I'm going to do, I'm going to just write down these numbers on the side. N1 is equal to 100 and X1 is equal to 15. N2 is equal to 150 and X2 is equal to 12 and alpha is equal to 0.05. If I do that, I have all the things, and I'll be able to use the space in the on the screen. So you're testing whether they have the same rate versus no, or same proportion versus no. So let's go ahead and take the background off and erase these guys. Great. Now, let's see, I want to bring the formulas down too. Before I forget, let me write down the formulas that I will need. Z star is equal to P1 hat minus P2 hat minus P1 minus P2, all of it divided by square root of P hat Q hat over N1 plus P hat Q hat over N2, and P hat is equal to X1 plus X2, okay, divided by N1 plus N2. And P hat is, by the way, called the pooled sample proportion, okay? It's called pooled sample proportion. And you know, P1 hat is equal to X1 over N1, and P2 hat is equal to X2 over N2. And then let's move down. I'm going to get the confidence interval 2. P1 hat minus P2 hat plus or minus margin of error. And the margin of error is E is equal to Z sub alpha over 2 times square root of P1 hat. This should be Q1. Q1 hat divided by N1 plus P2 hat Q2 hat over N2, and this goes all the way. And let me make sure that P1 hat, Q1 hat, and 1 this all forward to perfect. So now let me go ahead and take the screen off. Now I can do the problem. It may look a lot of information, but please bear with me. It's not a big deal. You'll see. I'm going to do the problem step by step, and you should be able to follow along. Now, step number 1, normality condition. Okay. Technically, you are supposed to have NP N1 P1 greater than equal to 10, N1 Q1 greater than equal to 10. Similarly, for N2 P2, N2 P2 greater than equal to 10, N2 Q2 greater than equal to 10. However, we don't know what is P proportion for the first group. We don't know what is proportion for the second group really. Okay, population proportions. Remember, P is the proportion for the population and P hat is the proportion for the sample. So these are the very basic things I have talked about previously many times. P is the proportion for the population, P hat is the proportion for the sample. Mu is the mean for the population, X bar is the mean for the sample. Sigma is the standard deviation for the population, S is the standard deviation for the sample. So now here, P1 is going to be the proportion for group 1 and P2 is the proportion for group 2. So you have to be able to relate these symbols in the context of multiple populations. So since we don't know, we are kind of going to assume that expected value from the sample is greater than or equal to 10, which is true. That's going to be done by N1 P1 hat. Okay. Now N1 is 100. Okay, 100 times P1 hat is X1 over N1. Remember, P1 hat is X1 over N1, which is 15 over 100. So it's going to be 15 over 100. Okay. If you do the multiplications, is greater than, oops, not 100, greater than or equal to 10. So we are good there. Similarly, with Q and N1, Q1 hat, which is 100 N1 times Q1 is going to be 1 minus P1. Q1 hat is 1 minus P1 hat. 1 minus 15 over 100. Okay. If you do the calculation, you will see that's obviously greater than or equal to 10. In exactly the same way, we are going to be doing it for N2 P2 hat, which is going to be N2 is 150 times P2 hat is 12 over 150, because 12 women out of 150 Mexican American women surveyed that said they smoke, greater than or equal to 10, and N2 and Q2 hat is going to be 150 times 1 minus 12 over 150, which is also greater than or equal to 10. So NP and Q scenarios are satisfied. And then we need to ensure that they are independent. So we kind of make the assumption that Mexican American women are independent of Caucasian women or vice versa, right? So the two groups or two populations are independent of each other. Two populations are independent of each other. So condition one, assumptions are clear. There is a bit involved in the assumption that you have to show NP and Q greater than or equal to 10, both of them for population one. You have to show NP and Q greater than or equal to 10 for population two. Okay, and since we don't know P, we used P hat. Since we don't know P here, okay, we used P hat. All right, that's about it. P hat is x1 over x over n, or in this particular case, x1 over n1 or x2 over n2. Now, step number 2 is going to be your null hypothesis and alternative hypothesis. Null hypothesis is that the proportion of women who smoke is the same for both the populations. That means Mexican American women versus Caucasian women. So P1 is equal to P2. That means they are the same, no difference. That's the null hypothesis, which goes with the assumption that null hypothesis always includes the equality. Null hypothesis always includes the equality. Whereas alternative hypothesis in this case that they are different. So that means P1 is not equal to P2, which right away should tell you that we are going to do a two-tail test. Two-tail test. We are going to do a two-tailed test that P1 is not equal to P2. Remember, P1 is the proportion of the first group, proportion of the white women, population proportion, and P2 is the population proportion for the Mexican American women. We are comparing to see whether they have the same smoking rate. Basically, in a nutshell, which I probably should have said at the beginning of the problem, in a nutshell, if you forget about all this mathematical mumbo jumbo, is very simple. What you are trying to figure out, do more white women smoke compared to Mexican women? A bigger percentage of white women smoke compared to Mexican American women? So this is kind of how you'd ask as a layman this question. Do a bigger percentage of white women smoke compared to Mexican American women? That's what you're trying to answer here. And to prove or to show that, we are going through a lot of details. So that's your null and alternative hypothesis. And your test statistic is going to be this guy. So let me write it down. Z star is equal to P1 hat minus P2 hat minus P1 minus P2, all of it divided by square root of P hat Q hat over N1 plus P hat Q hat over N2. Now P1 hat, we know we already used it. P1 hat is equal to X1 over N1, which is 15 over 100, which is 0.15. And P2 hat is X2 over N2, which is 12 over 150, which is 12 over 150. What number is it? 12 divided by 150, which is 0.08. 0.08. So remember this. So P1 hat is 0.15, P2 hat is 0.08. Then Q1 hat is going to be 1 minus P1 hat. 1 minus P1 hat is equal to 1 minus 0.15 is equal to 0.85. Similarly, Q2 hat is going to be 1 minus P2 hat is equal to 1 minus 0.08 is equal to 0.92. So these are two numbers you'll need, this one and this one. this one, and this one. So we just need to plug in these values here. Oh, okay, sorry. We don't plug in here. We actually need to find more. P hat. P hat is the pooled proportion, which is x1 plus x2 divided by n1 plus n2. Okay. X1 is 15 plus x2 is 12 divided by n1 is 100 plus n2 is 150. So 15 plus 12 is 27 divided by 250. So 27 divided by 250 is 0.108. Is 0.108, your p hat. P hat is 0.108. Your Q hat is going to be 1 minus P hat, which is 1 minus 0.108. That's going to give you 0.892. 892. Now P hat, Q hat, which is something I will need. So I'll just get that value. P hat times Q hat is 0.108 times 0.892 times 0.108, there's going to be 0.0963 is equal to 0.0963. Okay. Now I just plug in these values. P1 hat minus P2 hat. P1 is 0.15 minus P2 is 0.08 minus P1 minus P2. Look, P1 is equal to P2. If you have P1 is equal to P2, look here, P1 is equal to P2. If you subtract P2 from both sides, you're going to get P1 minus P2 is equal to 0. So the second term, this term is actually 0. And the bottom is going to be square root of this number, P hat, Q hat, P hat, Q hat, 0.0963, 0.0963 divided by 101, right? Plus 0.0963 divided by 150. And take the square root of the whole thing. So your Z star is going to be 0.15 minus 0.08 is 0.07 divided by this whole number. And what does it come out? Let me do the calculation. So let's use the thing. 1 divided by 100 is this, plus 1 divided by 150 is this, times 0.0963, and you take the square root of it to the power 0.5, enter, 0.04. 0.04. This comes out. Let me double check the calculation just to make sure that I haven't made any mistake. 1 divided by 100 plus 1 divided by 150 is this. Multiply it by 0.0963, which is this, to the power 0.5, which is 0.04. Okay. So 7 divided by 4 is 1.75. So your Z star for test statistic comes out to be 1.75. And let me put it inside a green box so that you can see it. Folks, my apology. It looks like a lot of calculation, but it's really, once you get the hang of it, it's not as bad. I'm going to do another problem, actually 2-3 problems easily, so you'll get the hang of it. It's not a big deal. All right, don't be scared by this. Now step 4, I need to find the critical region. Now critical region, my alpha is 0.05, right? We are gonna have to consider 2 tails because we are dealing with P1 is not equal to P2, so it's going to be 0.05 over 2, which is 0.025. Okay. So if I draw the bell-shaped curve, so associated with an area of 0.025, okay. This is 0.025, and this is 0.025, right? And as you probably remember, it is negative 1.96, right? And positive 1.96. Okay. I'm not going to look at the value. I think I remember it. Negative 1.96 for 0.025 and positive 1.96. This is one of the standard values. For 0.05 is negative 1.645. All right, so your critical regions are going to be, negative infinity to negative 1.96 union 1.96 to positive infinity. Okay, so from here to the left, from here to the right, and if I use highlighting, so this is what we are talking about, and this is what we are talking about, right? Now, that's your step 4. Now, step 5 is the conclusion. Okay, step 5, conclusion. Now, does your test statistic fall in the critical region? Is 1.75 to the right of positive 1.96 or to the left of negative 1.96? Obviously, this cannot be on the left. It's a positive number. It cannot be on the left because it's a positive number. Can it be on the right? 1.96 is right here. So your 1.75 would be somewhere here, 1.75. So it doesn't fall in the critical region. Z star, the test statistic, 1.75 is not in the critical region. Therefore, do not reject the null hypothesis. Do not reject the null hypothesis. What? That P1 is equal to P2. That means the proportion of white women that smoke is the same as the proportion of Mexican American women that smoke. And that's it. That's probably the most crowded screen we have ever had in the semester. But let me kind of summarize it so that you can see things. Step number 1, your normality condition. You show that expected value of the samples is greater than or equal to 10, which is this for the first population and the second population. So N1 P1 hat, N2 Q2 Q1 hat, N1 Q1 hat, and both of these has to be greater than or equal to 10. Similarly, N2 P2 hat greater than or equal to 10, and 2 Q2 hat is greater than or equal to 10. Two populations are independent of each other, okay? They are independent, so they don't influence each other. Of course, whether Mexican American women smoke is not going to be influencing the white women or vice versa, right? Now, next is this P1 null hypothesis, which is P1 is equal to P2, okay? Null hypothesis is P1 is equal to P2. That means the proportions are the same. And the alternative hypothesis is that P1 is not equal to P2. That means proportions are not the same. They're different. That means percentage of women between these two groups who smoke are the same versus not the same. Now, test statistic, this is the test statistic that we use, okay? This is this formula, and P1 hat, P2 hat, which is P1 is X1, N1, P2 is X1 over N1, P2 hat is X2 over N2, which we did the calculations here. You can see them. And Q1 hat is 1 minus P1 hat, which is this. Q2 hat is 1 minus P2 hat, which is this. I don't think I used these numbers, even though I calculated them. Now, we need to find the pooled sampling, which is P hat. That's X1 plus X2 divided by N1 plus N2. And that's 0.108. From that one, we find P hat. Okay, then we found Q hat and multiply these numbers. And just why did we need these numbers? Because we had to put this in here in the formula. So P1 hat 0.15, P2 hat 0.08, and then P1 minus P2 is 0 because our null hypothesis, the assumption is that proportions are the same. P1 is equal to P2. So P1 minus P2 is equal to 0. If I subtract P2 from both sides, I'm going to get P1 minus P2 is equal to 0. Now, if I did the calculation by plugging in these numbers, P hat, Q hat, I have it here. P hat, Q hat, I have it here. N1 is 100, N2 is 150. And if we do the calculations, I get Z star equal to 1.975. Then the rest is very straightforward. Alpha over 2, because we are doing two-tailed test. So 0.025, and that gives us critical regions. Negative, starting from negative 1.96 to the left and starting from positive 1.96 to the right. All right. And if I did the calculations, this is what I get. And conclusion is that 1.75, the test statistic, it does not fall in the critical region. It doesn't fall here, nor does it fall here. Therefore, we do not reject the null hypothesis that the proportions are the same for these groups. So we don't have enough statistical evidence that they are significantly different in terms of smoking habits. Okay. Now, if you were to be a statistician and you are trying to convey your results to your supervisor or manager who doesn't know statistics. So as a statistician, you cannot be giving all these numbers to your manager. Your manager will say, okay, you're crazy, all right? Because the manager doesn't know, they're into management. So you have to explain it to them in a way that's ordinary people would understand, okay? So you'd say, oh, I have done the statistical analysis. There is not really much significant difference between white women and Caucasian women in terms of their smoking habit, okay? Or even simpler way, white women and Mexican American women, they kind of smoke at kind of like the same amount or same rate, okay? That's something that your manager could consume, or that's something that a doctor, a manager at a doctor's office or a hospital rather would be able to consume that information. Okay, maybe at the hospital the management is probably more knowledgeable about statistics. I take it back. So they probably would understand a little bit of details, but still, in a meeting you have to make your presentation. You'd say, yeah, I have done the statistical analysis on the data sets, and there is not really much difference in terms of smoking habits for white women versus Mexican American women. So that's something that everybody will be able to consume. All right. Any question about this lengthy problem, anybody? Anybody, any question? Alicia, how much of it made sense to you?
Well, Professor, probably another one would help.
Okay, sure. Yeah, go ahead.
It made sense, but it was just like a lot to take in at one time.
Yes, I completely understand. I plan to do at least 2 more problems, okay? at least 2 more. In the second one, you'll start to get a bit more comfortable. In the third one, you'll even get more comfortable. If time permits, I might even do fourth one, all right? So that you get plenty of examples. And there is the video, I'm recording it, so you can go ahead and watch it. Now, I did the hypothesis testing, but I didn't do the confidence interval. Do you notice that? So now I'm going to do the confidence interval for this one. Okay. So let's clean up the screen first. Big mess. Okay. Now confidence interval is very easy. Okay. Your z sub alpha over 2, which was 1.96. All right. P1 hat minus P2 hat. P1 hat minus P2 hat is equal to P1 hat was 0.15 and P2 hat was 0.08. So the difference is 0.07. So this number is 0.07. Now, I just need to find the margin of error. So E, or the margin of error, is 1.96 times square root of P1 hat Q1 hat, no, it's not Q2, P1 hat Q1 hat, which is 0.15, P1 hat 0.15 times Q1 hat is going to be 1 minus 0.15, which is 0.85 over N1, which is 100. Plus P2 hat, which is 0.08 times Q2 hat, which is 1 minus 0.08, which is 0.92. All of it divided by N2, which is 150. And let me do that calculation, and that will give me my margin of error. So 0.15 times 0.85 divided by 100. Let me use a parenthesis with this calculator. This is crazy calculator. So 0.15 times 0.85 divided by 100, close parenthesis, plus open parenthesis 0.08 times 0.92 divided by 150, close parenthesis, then close parenthesis to the power 0.5, then multiplied by 1.96. So this is going to be 0.0823. Okay, so your margin of error is 0.0823. And let me double check it just to make sure that we are okay. So 1.96 times, open parenthesis, 0.15 times 0.85 divided by 100 plus 0.08 times 0.92 divided by 150, okay, to the power 0.5. Yes, it is correct. So margin of error is 0.0823. So my confidence interval is going to be P1 hat minus P2 hat plus or minus E. My P1 hat minus P2 hat is 0.07 plus or minus E 0.0823. You know, just for simplicity, I'll just take up to 0.08. There is no point of going higher than 0.08. So we'll just stop there. So my confidence interval is going to be 0.07 minus 0.08, comma, 0.07 plus 0.08. If you do the math, 0.07 minus 0.08 is going to be negative 0.01, comma, 0.07 plus 0.08 is 0.15. So the confidence interval, okay, 95% confidence interval, right? Because significance level alpha is 0.05, okay? Remember, alpha is 1 minus the confidence level. So 95% confidence level we have on this interval, which goes from negative, so pay attention, it goes from negative 0.01 to 0.15. So if you draw it on the number line, if this is 0 and this is where your 0.15, you know negative 0.01 is somewhere here. So it goes from here to here. So 0 is included. So if I highlight it, it's gonna be from here to there. All right, so 0 is included. Now, what is the significance of having 0? This confidence interval tells you that, remember, we are trying to test P1 is equal to P2. This tells you that P1 minus P2 is equal to 0, right? This confidence interval tells that P1 minus P2 is equal to 0. It contains 0. That means the proportions could be equal. So we kind of get the same conclusion as we did from the hypothesis testing. Just because the inclusion of 0 in this interval, just because we have it, we can assume that it is possible that two proportions are equal, or equivalently, P1 minus P2 is equal to 0. Remember, this one and this one, they are equivalent statements. P1 is equal to P2 is the same as saying P1 minus P2 is equal to 0. So our, look, we use P1 hat minus P2 hat here. Our confidence interval includes the 0, meaning that we agree with the conclusion that we came up with the hypothesis testing. That means proportions are equal at 0.05 significance level. Or equivalently, in the confidence interval case, I'm 95% confident that the true proportion difference for these two populations is contained in this interval, which is 0 in this case. The difference we are assuming to be 0, that means they are the same. So that's the whole story. And it's a bit of an involved calculations. Hopefully you don't get too overwhelmed by it. Any question, anybody, about this guy? Anybody? Anything that I could answer before I move on to the next problem? No questions? Everybody okay? All right. Okay. Now let me go ahead and work on the next problem. So the first one was about the smoking difference between Mexican American women and white women. Let's see, the next problem is about Daca students. Daca stands for Deferred Action Children, something arrival, I think. Oh, Deferred Action, here it is. Deferred Action for Children, Childhood Arrivals, Daca. Also known as Dreamer students, okay? Daca is Deferred Action for Childhood Arrival. It's the children who came here as minor with their parents by crossing the border, which is called Daca. Now, let's go ahead and work on this problem. So Jean K. Park, a Harvard undergrad and the first Daca student to win the prestigious Rhodes Scholarship. Okay, Rhodes Scholarship is a prestigious scholarship, and he's the first Daca student to win it. I think that was several years ago when I made the problem. Time flies. It's been probably, I don't know how many years, maybe 6, 7, 8 years, who knows. All right. In today's political climate under the current president, oh, maybe I made the problem during our lovely President Trump. Daca students are under pressure for their legal status. So to get a feel for public opinion in two of your neighboring cities named M and S, you surveyed 200 people in city M with 125 supporting Daca and 300 people in city S with 250 supporting Daca. So what you're trying to do, you're trying to basically find out what kind of support in the general population people have for Daca students. And you want to compare the support level for two different cities, okay? One is M, let's say M for Marina or Monterey, maybe. M for Monterey and S for Salinas, okay? So you want to find the support level at two different cities, Monterey and Salinas, and try to compare them. That's exactly what you're trying to do. First, create a confidence interval for the difference in population proportions for the two cities. Then test the claim that the city has higher proportion of population supporting Daca. Okay. Then test the claim that I didn't say any, interesting. Did I say any significance level here? I don't see it. So since I haven't mentioned it, let's do it for 0.05, easy. 0.05 or 5% significance level. Okay. Test the claim that in city S has a higher proportion of people supporting Daca. So now I'm going to write down these data points, honestly, guys, before I lose them. So let's say city S is Salinas, okay? City 1, X1 was 250. X1 is equal to 250. And N1 is equal to 300. City M is Monterey. X2 is 125, and N2 is 200. And alpha is equal to 0.05. And we are going to have to do the same. I'm going to copy those formulas for you here. Z star is equal to P1 hat minus P2 hat minus P1 minus P2, all of it divided by square root of P hat Q hat over N1 plus P hat Q hat over N2. And P hat is equal to pooled proportion X1 plus X2 divided by N1 plus N2, right? And then let me just even write down the formula for confidence interval P1 hat minus P2 hat, okay, plus or minus E, or margin of error E, is equal to Z sub alpha over 2 times square root of P1 hat Q1 hat over N1 plus P2 hat Q2 hat over N2. And that's all the formulas that we need, okay? And now let's go back to the problem, which is this problem, by the way. And we have all the numbers. So just to summarize what we are trying to do, we are trying to figure out, is there a statistically significant difference in support level for Daca students between Salinas and Monterey? Or equivalent, we are asking, do more Salinas people or a higher percentage of Salinas people support Daca compared to Monterey, okay, or Monterey? That's what we are trying to find. Now is still the same process. We are going to walk through the same steps. Step 1, okay. Our N1 proportions, N1 P1 hat is greater than or equal to 10. We need to show that, okay. So look, N1 is 300 right here times 250, oops, T over 300, which is greater than or equal to 10, by the way. You can do the calculations. N1 Q1 hat is equal to 300 times 1 minus 250 over 300. And you can do the calculation. That's also greater than or equal to 10. And for N2 P2 hat is equal to 200 times 125 over 200, which is greater than or equal to 10. And N2 Q2 hat is equal to 200 times 1 minus 125 over 200, and you can do the calculations. That's also greater than or equal to 10. All right. So we are assuming, we are ensuring normality. Now we are assuming that these two populations of Salinas and Monterey are independent of each other. So population, that's kind of something we have to assume. Populations are independent of each other. Populations are independent of each other. Step number 2, your null and alternative hypothesis, okay? Your null hypothesis is that P1 proportion of Salinas, okay, is the same as the proportion of Monterey. And your alternative hypothesis, however, here, you're not testing whether they are different, but you're testing whether Salinas has higher percentage of people supporting Daca. So we are testing P1 is greater than P2. That means whether a higher percentage of people in Salinas support the Daca students or Daca folks, okay? Daca folks, many of them are students, by the way, because they are young. When they came here, they were probably 5-year-old or 7-year-old or 12-year-old kids, right? So now the next one is going to be step 3, the formula, P1 hat. So I'm going to do the little calculation. P1 hat is equal to 250 over 300, okay? So 250 over 300, 250 divided by 300 is 0.833. So I'll just put 0.83. Similarly, P2 hat is gonna be 125 over 200, 125 divided by 200 is 0.625. 0.625. Okay. What else I need? So I have P1 hat minus P2 hat. Now P hat, pooled sampling, I have to do it. Pooled sampling is P hat, which is x1 plus x2 divided by n1 plus n2. So P hat is gonna be x1 is 250 plus x2 is 125, all of it divided by n1 300 plus n2 200. So 375 divided by 500, 375 divided by 500, which is 0.75. So your p hat is 0.75. And q hat is gonna be 1 minus p hat, which is 0.25. So we have everything for this formula. So we are gonna, instead of writing the entire formula, I'm just gonna write out the values. So P1 hat minus P2 hat. P1 hat is 0.83. Let's take one extra digit, 0.833, minus P2 hat is 0.625, which is this, 625, minus P1 minus P2. So remember, P1 is equal to P2, that's our assumption. P1 is equal to P2. If you subtract P2 from both sides, you're gonna get P1 minus P2 on the left. This and this cancel out, 0. So this is gonna be 0. Divided by square root of P hat Q hat. P hat is 0.75. So 0.75 times 0.25. So let's see, what do I get? 0.1875. 0.1875 divided by 300 plus 0.1875 divided by 200. So 75 times 0.25 is 0.1875, okay. Times, open parenthesis, 1 divided by 300, close parenthesis, plus, open parenthesis, 1 divided by 200, close parenthesis, close parenthesis, to the power 0.5. Oops. Delete. I made a mistake. I'm trying to do the calculation. Okay, I have to clear it. So give me a second. Let me do the calculation again. 0.1875 times 1 divided by 300 plus 1 divided by 200, then this close parenthesis to the power 0.5. Okay, 0.0395. So Z star okay, Z star is gonna be 0.0395 in the bottom, and on the top 0.833 minus 0.625 is 0.208, 208. So that gives me Z star is equal to 0.208 divided by 0.0395, which is 5.626. 5.26. So remember this value. Okay. Please double check this calculation. By the way, I'm guessing I haven't made any mistake. All right. So that's my test statistic Now the next one is pretty straightforward. Bell-shaped curve. This time we're going to do one tail test. Okay, which tail? Right tail. Why is it right tail? Because look, we're doing greater than. So this is going to be 1.645. So your critical region is going to be from 1.645 all the way to positive infinity. Okay, so everything to the right. So we are talking about everything from here to the right. Now, look, 5.26, does it fall in the critical region? It does, it's somewhere here, 5.26. So your conclusion is gonna be test statistic Z star is equal to 5.26 falls in the critical region. 5 to infinity. Therefore, we reject the null hypothesis. We reject. So we reject H naught, that the percentage of people in Salinas who support Daca is the same as the percentage of people in Monterey who support Daca. They are not the same. Okay, we are claiming that it is greater in Salinas than it is in Monterey. Exactly same calculation. So once again, let me summarize what I did. So what is the problem here? The bigger problem is we are trying to answer the question whether a higher percentage of people in Salinas support Daca compared to Monterey. That's what we are trying to answer. Again, whether a higher percentage of people in Monterey, Salinas, support Daca compared to Monterey. And in the first step, what we go through is the normality conditions. Since we don't know p hat and p1 and p2, we just use the expected value p1 hat, p2 hat. Okay, on the average, can we expect more than 10? All right, so which is this we do. And we do the calculations here. And we assume that the population of Monterey and Salinas are independent of each other. Our null hypothesis is that the proportion of support or percentage of support for both the cities are the same, okay? And our alternative is that percentage of support in Salinas is greater than percentage of support in Monterey. And your test statistic, you want to find the P1 hat and P2 hat and subtract P2 from P1, and then P1 minus P2 is 0 because P1 is equal to P2. That's the default assumption. If you subtract P2 from both sides, you get P1 minus P2 is equal to 0. And in the bottom, you find the P hat, which we do here, P hat, and it gives me 0.75, Q hat 0.25. So P hat, Q hat is 0.1875. So we just plug it in here, and 1 is 300, and 2 is 200. And I do the simplification. I get Z star is equal to 5.26. And then I do the critical region. My alpha is 0.05, right? Which we did assume. Alpha is 0.05. And for that, my critical value is going to be 1.645. So my critical region is going to be from 1.645 to infinity. Okay. Now the test statistic, which is 5.26, does in fact fall in the critical region. Therefore, we reject the null hypothesis that the proportions for two cities are the same. That means we are saying that we are at 0.05 significance level. We are saying that proportion of support for Daca in Salinas is higher than proportion of support for Daca in in Monterey. Now we are going to use this formula. P1 minus P2, that value is, what was it, 0.208. So 0.20, let me use a different color. 0.208 plus or minus the margin of error. And margin of error is pretty straightforward, which is 1.645 times square root of these values. P1 had 0.833, okay. So 1 minus 0.833 is 0.167 times 0.167 divided by N1, which is 300, plus is still under the square root, by the way, guys. P2 hat is 0.625. 1 minus 0.625 is 0.375. 0.625 times 0.375, all of it divided by 200. Okay. So let's do the calculation and then I'll get a number for you. So 1.645 times open parenthesis 0.833 times 0.167 divided by 300 plus open parenthesis 0.625 times 0.375 divided by 200, and that concludes this. And then I need another parenthesis to the power 0.5. It gives me 0.0665. Okay, is 0.0665. Now my confidence interval is going to be 0.208 plus or minus let me round it to 0.067, okay? 0.067. So it's going to be 0.208 minus 0.067 is equal to 0.141, okay? I'll just leave it 0.14, comma, 0.208 plus 0.067, which is 0.275, 0.275, okay? Okay, maybe I should keep the 1.275. All right, so actual percentage falls between what? 14.1% and 27.5% between these two numbers. So our confidence interval is positive, okay? That means it does not include the 0. So that means it's positive, means which is telling you P1 is greater than P2, because we are dealing with P1 minus P2. This is P1 minus P2, P1 minus P2. It's positive, meaning it includes the condition, or it's saying that proportion in Salinas is greater than proportion in Monterey. Had it included 0, we couldn't conclude. Had it included 0, we could not conclude. That's what it is. Okay. So it kind of coincides with what we came up with by hypothesis testing. So you can do the testing of a claim by using the standard procedure for hypothesis testing, or you could do it similarly using the confidence interval. That's what it is. Now, guys, do you feel slightly more comfortable compared to the last time, compared to the last problem?
Yes.
Okay, good to hear that. Okay. Now, let me go ahead and clean up the screen. And let's move on. So these are the only two problems that I have had from hypothesis testing for proportion. So remember PMS, we are not doing S. Hypothesis testing for proportion and hypothesis testing for mean. So the next one is going to be hypothesis testing for mean. Again, exactly the same procedure, nothing out of the ordinary. Now for the mean, we are dealing with two situations where you know sigma versus you don't know sigma. Okay. Something went wrong. My screen is not showing my rest of the pages. Okay. Okay. This for hypothesis testing involving population mean there are two scenarios. When you know sigma and when you don't know sigma. If you know sigma, you use z-score for, right? And when you don't know sigma, you use t-distribution. Okay. Now, let's do one problem, then we'll close it. So we are going to do the t-distribution one, not the z-score one. That means we don't know population standard deviation. T-distribution means we don't know population distribution, population standard deviation. So assumption is the same. Simple random sampling for both of them. Samples are independent of each other. Sigma 1 and sigma 2 are unknown, and populations are normally distributed. Hold on 1 second, guys. Okay. All right. So let's go ahead and work on this problem. It's pretty much very standard. Once you know one of them, the others are pretty standard. So we are going to do the t-distribution one when we do not know sigma 1 and sigma 2. When we say I don't know sigma, that means I either don't know sigma 1 or I don't know sigma 2 or both. Okay. So we are going to assume that sigma 1 and sigma 2 are unknown. So let's write down the formulas here. So let me take this guy up here. T star is equal to x1 bar minus x2 bar minus mu1 minus mu2, all of it divided by, this one is easier, by the way, s1 square over n1 plus s2 square over n2. Okay. And E is the margin of error, mu1 minus, this should be hat, mu1 hat minus, oops, sorry, not mu1 hat, sorry, I meant x1 bar minus x1 bar minus x2 bar plus or minus E. There is a mistake, a typo here. This should be x1 bar minus x2 bar. Sorry about that. Plus or minus E. And E is T sub alpha over 2 times square root of S1 square over N1 plus S2 square over N2. Now we can do this problem very quickly. Okay. We can do the problem very quickly. So let's go ahead and read a problem. All right. We're going to go ahead and read a problem. Then you will see what's going on. So let me just erase this guy. Okay. Okay, there are two problems here. We might be able to do both of them because these problems are pretty straightforward. At Hartnell College, for a sample of 50 students, the average time to graduation is 30 months with a sample standard deviation 4 months. While at Cabrillo College, for a sample of 30 students, the average graduation time is 28 months with sample standard deviation 5 months. At 0.05 significance level, is there a statistically significant difference between the two population averages? Also create a confidence interval to compare your finding. So what you are asking here, the question that you're asking is that, hey, are Hartnell students taking longer time to graduate compared to Cabrillo students? That's what you're asking. So I'm trying to simplify the problem for you. You're trying to find out, on the average, are students at Hartnell taking longer time to graduate when you compare it with that of Cabrillo College? So that's the thing. So now let's go ahead and do the problem. It's very, very simple, very straightforward. You just need to identify things. So your N1, I'm going to write down these numbers so that you can, let's say Hartnell College is population 1, Cabrillo is population 2. Your N1 is equal to 50. Your X1 bar is equal to 30. Your S1 is 4. Where did I get it from? At Hartnell College, a sample of 50. Okay. The average time to graduation is 30 months. That's X bar. So N1 is 50. N1 is 50. X1 bar is 30. With a sample standard deviation, S1 is 4. Okay. While at Cabrillo College, okay, which is going to be your N2, what is your sample size? 30 students. X2 bar is 28, and S2, or sample standard deviation for population 2, is 5 months. Okay, and your alpha is equal to 0.05. What are you testing? Is there a significant difference? That means either they are equal or not equal. So let me take the background off so that you can go ahead and work on it. Now you will see, third time around, these problems are going to look easier. Step number 1, okay? So our assumption is going to be, well, sample sizes here we can assume. I still kept thinking about proportion. Our sample sizes N1 and N2, both of them are greater than or equal to 30. Okay, N1 is equal to 50, which is greater than or equal to 30, right? And N2 is equal to 30, which is also greater than or equal to 30. So both of these populations, sampling distributions, are bell-shaped or normal. Okay. Sampling distribution of size of 50 for the first population is normal. Sampling distribution for the second population is also normal because sample size is 30. So we are good there. And we are assuming that they are independent, populations are independent. Are independent. And implicitly, we are assuming that we are doing simple random sampling, SRS. Simple random sampling, that means no bias or nothing. So that's step number 1. And step number 2 is going to be null hypothesis that mu1, that the average population for Hartnell is the same as the average graduation time for Cabrillo. Okay, mu1 is equal to mu2. And your alternative hypothesis, by the way, is going to be that mu1 is not equal to mu2. That means the average graduation time for Hartnell students is not the same as the average graduation time for Cabrillo students. Step number 3, easy. I have all the numbers, x1 bar, so I'm going to plug it in here. T star is going to be equal to x1 bar, which is 30, minus x2 bar, which is 28, minus mu1 minus mu2. Mu1 is equal to mu2. Mu1 is equal to mu2. If you subtract mu2 from both sides, you get mu1 minus mu2 is equal to 0. So there's going to be 0. Divided by square root of S1, 4 square divided by S1 is the sample standard deviation for the first group divided by N1, which is 50, plus S2 square, S2 is 5. Okay, was it 5? Simple, yeah, 5 months. So 5 square over N2, which is 30, which gives me 30 minus 28 is 2, square root of 4 square is 16 over 50 plus 25 over 30. I can simplify it slightly more. 2 over square root of 8 over 25, because 2 goes into 16, 8, 2 goes into 50, 25 times, plus 5 goes into 25, 5 goes into 36, or 5 over 6. And if I did the math, let's do the math here. Okay, 8 divided by 25 plus 5 divided by 6 to the power 0.5, 2 divided by 1.86. 1.86. Let me double check the calculation, guys. 5 divided by, 8 divided by 25 plus 5 divided by 6 to the power 0.5, 2 divided by this is 1.86. So your T star is equal to 1.86. So remember that number. Now step number 4, okay, which is going to be your critical region. So let's draw it here. Critical regions. Remember, T distribution is a bit stretched to the right and left. Now we are going to be doing two-tail test because it's not equal to. So area in one tail, alpha is 0.05, right? So alpha over 2 is going to be 0.025. Area in one tail is 0.025. Area in two tail is 0.05, right? So left side has 0.025, the right side has 0.025. So now what is this value and this value? Now we need to find the degrees of freedom. Degrees of freedom, I think, I have a feeling I'm right. It is smaller of the two, not the bigger of the two. So N1 and N2, you have N1 and N2, all right? Degrees of freedom is gonna be smaller of the two, okay? So 30, so N1 is 50 and N2 is 30. So the smaller of the two is this, 30. So this is gonna be 30. So this is where I am not 100% sure whether I subtract 1 or 2. I forgot. Let me see if I wrote it down here. Let me just double check. Okay, I don't think I wrote it down. It's the smaller of the two, all right? Okay. I'm very sure it's smaller of the two, but what I forgot is whether I subtract 1 or 2. I think I subtract 1. So I'll just take it as it is. So 30 minus 1 is going to be 29. So my degrees of freedom, DF, is equal to 29. All right. So there is one bit of confusion here, which is not a big deal really so much, and I'll not be penalizing you for that, or I'll clarify it later. Let's put it that way. Whether I subtract 1 or 2, I think I subtract 1 because it's one population. I'm taking the smaller sample size. So it's going to be 30 minus 1 is 29. Now you go back to your t-distribution table. Area in one tail 0.025, area in two tails 0.05. Then you go down the first column and look at 29. So you guys also look for this value, everybody. And I'm gonna look for it here too on my end. And that value is going to be distribution. Where are you? Right here, critical distribution. Degrees of freedom is 29, area in two tails 0.05, area in one tail is 0.025. So that gives me 2.045. So this is gonna be 2.045. This is going to be negative 2.045. That's what it is. Okay. So your critical regions become nothing but, so your critical regions becomes negative infinity to negative 2.045 union 2.045 to positive infinity. Okay. Negative infinity to negative 2.045 and 2.045 to positive infinity. And step number 5, your critical conclusion is this. Your test statistic 1.86, Z star is equal to 1.86. It doesn't fall either here, nor does it fall here, okay? It doesn't fall either here, nor does it fall here, okay? Therefore, so it's probably somewhere here, 1.86. Does not fall in the critical region. In the critical regions. In our case, we have two regions, right? Therefore, we do not reject the null hypothesis that what? mu1 is equal to mu2. We do not reject the null hypothesis that mu1 is equal to mu2. That's what it is. So that's the whole story. Now, to find the margin of, confidence interval, we need to find the margin of error. It's the exact same thing. You do the normality conditions, you do the null and alternative hypothesis, you do the test statistic, you do the critical region, and you come to the conclusion. And you can do the p-value too, right? If you want, p-value is going to be everything to the right of this dotted line, which is greater than alpha over 2. So you do not reject the null. If it were to be right here, everything to the right of this point would be less than alpha over 2. So you will be rejecting the null hypothesis. So you can do the p-value calculation as well in exactly the same way. Now let's go ahead and do this margin of error calculation. T sub alpha over 2, we found it 2.045. So it's going to be 2.045 times square root of S1 square over. So that number, I think I have it. Oh, let me check my calculator. Do I still have it? Yeah, I have that value. This is, by the way, 1.07. Okay. All right. 1.07. That is this denominator. Look, this is the same as this one in the formula. So your margin of error is going to be E is equal to 1.07 times 2.045, which is 2.18815. 2.18815, which is, I'm just going to write it here, 2.18 or 19. Let's see, make it 19. 2.19. So your margin of error is 2.19. So x1 bar minus x2 bar plus or minus e. x1 bar minus x2 bar is 30 minus 28, which is 2, right? 30 minus 28 plus or minus 2.19. So that's going to give me 2 plus or minus 2.19. So if you do the thing, it's going to be negative 2 minus 2.19 is negative 0.192. 2 plus 2.19 is 4.19. So your confidence interval is from negative 0.19 to 4.19, which obviously does includes zero. It includes 0, which says that it could be equal. That means that the means could be equal. It includes 0. That means that means could be equal. That's what it is. And it's the same conclusion that we came up with when we did the hypothesis testing. So the conclusion based on hypothesis testing is the same as the conclusion based on confidence interval. So we are doing the same conclusion. We are coming to the same conclusion. One based on the hypothesis testing, the process of hypothesis testing. Another is using the confidence interval. So that's another way of checking your validity or checking your sort of like sanity check, making sure that everything is okay. You're doing it all right. In both of these, you are getting the same answer. Now, if I had a confidence interval that's 0.19 to 4.19 instead of negative 0.19, then this does not include 0, right? In that case, it does not kind of conform with our conclusion that we don't reject the null hypothesis. We don't reject the null hypothesis means that it could be 0. That means the confidence interval should be including 0, which it does here. But had it been this, then we would have an inconsistency. So maybe we should check our calculations and find out what's going on. All right. Any question?
No question.
Okay, no questions. All right. Do you guys have a strength for another problem? One last problem? Exactly same thing. Oops. So Hartnell College, so I'm comparing Hartnell College. So the number of months they take to graduate. The second problem, a Hartnell College simulation 40 students reveals that they study 17 hours. Exact same thing compared to some other college, Cabrillo College. The Cabrillo College people are not going to be happy with me if they have left. So what did I do? Hartnell, 40 students, 17 hours, whereas standard deviation 2, Cabrillo, 40 students, 16 hours. No, it's pretty close. So they won't be unhappy with the standard deviation of 2.5. Is the exact same duplicate of the problem that I just did. Only thing is that in the last one, I compared average graduation time for Hartnell versus Cabrillo. And in this one, I compare average number of hours Hartnell students study per week compared to Cabrillo students. Okay, so the number of hours students study at Hartnell, I compare it with that of Cabrillo. Now, would you want me to go over the same problem? Exactly. If you have patience, I do as well. But if you feel that it's a lot of information, then I can stop. What do you guys think? I'll give you the choice. Should I go over this? Anybody wants to express their opinion? Jerry, what do you think? Should I go over the problem? Jerry, are you there?
Yeah, I'm here. I was just looking over the math stuff like right now. Yeah.
Go over it?
Yeah.
Okay, good. At least there is one person who is supporting going over it. So let's go ahead and go over this. They'll give you a little bit. Okay, great. I have 2 supporters. All right, thank you. Thank you, Alicia. So let's go ahead and do the problem. Oh, where is my formula? I deleted all the formula. Let's see if I can get the formula. No, I'll get rid of it. I'll get the formula again. Okay. So at Hartnell College, a simple random sample of 40 students reveals that they study about 17 hours per week with simple standard deviation of 2 hours. While at Cabrillo College, for a sample of 40 students, the average is 16 hours per week with a simple standard deviation of 2.5 hours. At 0.05 significance level, test the at 0.05 significance level, is there a statistically significant difference between the 2 population averages? Also create confidence interval. So I'm just gonna write it out here. So let's say Hartnell is population 1 and 1 is 40. X1 bar is 17. S1 is 2. And 2 is also 40. X2 bar is 16. And S2 is 2.5. And alpha is equal to 0.05. Right? Now I'm going to take the background off. Step number 1, what we have got is this. N1 is equal to N2 is equal to 40, which is greater than or equal to 30. So normality condition is satisfied. And we are assuming that the populations are independent. And then we are also assuming that we are doing simple random sampling. That means without any bias or any prejudice. Okay, we randomly select people, completely randomly. So these things are good. Step number 2, our null and alternative hypothesis. Null hypothesis is that mu1, the average number of hours Hartnell students study, is the same as mu2, the average number of hours the Cabrillo students study. And alternative, we are testing if they're different, which is mu1 is not equal to mu2. That's what we are testing. And our test statistic, T star, is equal to x1 bar minus x2 bar minus mu1 minus mu2, all of it divided by square root of s1 square over n1 plus s2 square over n2. x1 bar, x2 bar, so 617 minus 16 minus mu1 minus mu2 is going to be 0 because mu1 is equal to mu2. That's the null option. And square root of s1, which is 2 square divided by 40 plus 2.5 s2. So s1 to 2.5 over 40. If I do the math, it's going to be 1 over square root of 4 over 40, which is 1 over 10, plus 6.25 over 40. And if I do the calculation, I get, let's see, 6.25 divided by 40 plus 0.1 is this, to the power 0.5, which is 0.506. 1 divided by the 0.506 is 1.975 or 1.975. So that's your test statistic. Now, step 4, your critical regions. Remember, our degrees of freedom is the smaller of the 2 minus 1, okay? Smaller of the two numbers. So we'll say minimum of n1, comma, n2 minus 1, okay? So minimum, in this case, both of the numbers are the same. So min is 40. So 40 minus 1 is 39, okay? So that's your degrees of freedom, DF. So that's my T distribution. So alpha is 0.05. So this is going to be 0.025 because we are doing two-tail test, right? And this is going to be my 0.025, right? So alpha is 0.05. Alpha over 2 is 0.025. Okay, great. Now, let's go ahead and do the problem. So now, what we are going to do, we are going to look at the degrees of freedom. So there is, I'm looking at the T distribution table. The table I have, it doesn't go to, it doesn't have 39. It goes from 38 to 40. So I'll take the closest value, okay? So maybe 40, I'll take 40. And that gives me 2.201, I think, 2.201, yes. So this is going to be 2.201 and negative 2.201. So your critical regions are going to be negative infinity to negative 2.201 union 2.201 to positive infinity, okay? Now, my test statistic, by the way, All right, my test statistic. By the way, since this degrees of freedom, actually we don't have it on the table. We don't have the exact values. So this is pretty close enough, okay? This is reasonably close. We are okay with it. There is no point of being concerned about it too much. All right, statistics by nature, it's an approximation. It is not an exact science like 2 + 3 = 5 always. We try to approximate things. So T distribution in and of itself is an approximation. That kind of is stretched normal distribution. So 2.201, so we are good there. Now, step number 5, does it fall in the critical region? Test statistic T star is equal to 1.975, does not fall in the critical region. In critical regions, okay, which are these two regions. Everything from here to negative infinity, everything from here to positive infinity. 1.97 is somewhere here, 1.97. 1.97 is right there. So it does not fall in the critical region. So what do? We do not reject the null. We do not reject the null hypothesis that what? mu1 is equal to mu2. That means Hartnell and Cabrio students study about the same. Now, if our calculation is correct in the confidence interval, we should include 0. Remember, include 0. Okay, it should be including 0. Keep that in mind, because we are saying that mu1 is probably equal to mu2. So again, we are going to do this. So what is this number? So my x1 bar minus x2 bar plus or minus margin of error, and E is equal to T sub alpha over 2 times square root of S1 square plus S2 square over N1 over N2. And T sub alpha over 2, we found it, guys, which is 2.201. Now times this value, I have it right here, and let me do the calculation again. It's gonna be 6.25 divided by 40 plus 0.1, and take the square root of it. That's 0.506. 0.506. So 0.506 times 2.201, right? 2.201. 0.506 times is 1.11. So margin of error is 1.1137. So I'll just leave it as 1.11. So now I plug in E here, x1 minus x2, x1 bar minus x2 bar is 17 minus 16 plus or minus the margin of error 1.11. 17 minus 16 is 1 plus or minus 1.11. If I do the math, 1 minus 1.11 is negative 0.11. See, negative is included here. So that means it's going to go to positive 2. 1 plus 1.11 is 2.11. So your confidence interval, this is your confidence interval. That's, by the way, 95% confidence interval. Now, this confidence interval does include 0, right? See, we are saying that it includes 0. So we are kosher from both sides. All right. We are kosher from both sides. Any questions, anybody? Anyone, any question, anything I could answer? All right, you guys survived the long lecture today. And this is the longest lecture we have had with a lot of constant information. It's not hard, by the way. It's just a lot of calculations. That's about it. The process, fundamental process, is something you have gone through in the single population hypothesis testing, confidence interval, and standard deviation. Hypothesis testing, confidence interval for single population, which you did for proportion, mean, and standard deviation. Now, in case of multiple populations, it's a bit more complicated. But interestingly, the next one is more than two populations. We compare two populations. When you are dealing with more than two populations, things are actually slightly easier. We use F distribution. So that one probably I won't cover here. So no worries. That's pretty much it that I will cover for the entire semester. Okay, we covered a lot of materials, by the way, guys, a lot of. But you have nothing to worry. Just do the homework, own homework that I opened already. You already have done it once. Just browse through those homework. The problems that you are having difficulties with, those are the ones you want to mark. And bring those to me on Wednesday. On Wednesday, I will not be covering anything new at all. So this is basically the end of new stuff. Okay? This is the end of new stuff, these materials. And on Wednesday, go over the review problems first, and then go over the homework problems and collect all the questions. Okay? I'll have 2 hours and whatever minute, 2.5 hours or so review for the final. Okay, you can ask me as many questions as you want, and please do make sure that you go over these problems early, because you cannot be waiting until the last moment. Okay, on the Sunday night before the test, right? The test is on Monday at 6 a.m. I'm going to open the test. You cannot be waiting until Sunday night and expecting that, oh yeah, I'm going to be doing okay. So go over these problems very quickly within the next couple of days, today and tomorrow and Wednesday. Bring in your questions, and I will be happy to answer any questions that you may have related to the class, of course. Anything before I move on, guys? Anybody has any questions? Alicia, any questions?
No questions, Professor, but thank you very much for all the information you've given us.
You're very welcome. All right, anybody else has any questions? Okay. If not, that's all for today. Thank you so very much. I'll be talking to you guys on Wednesday. Thank you.
Thank
Bye.
you. Bye.
Bye.